data moves fast, and sometimes you need to make critical decisions before the final numbers are in. Is the outbreak stabilizing? Are we hitting the peak? Q, our trusty math concept, the limit. A limit tells us what value a function is approaching as time goes on, even if it never quite gets there. That means as x gets close to a, fx gets close to L. Let's model an outbreak using a logistic function. Translation: the outbreak will eventually max out at 10,000 cases, even if we haven't reached that number yet. Pretty handy for planning hospital beds, right? Introduce a new vaccine or a mask mandate, and boom, that curve might change shape. You're not just watching numbers anymore. You're watching the limit shift. The rate of change tells us how fast cases are rising or slowing. Let's look at example 2. B. Represent daily cases. We calculate the average rate of change over a small interval. But when we shrink that interval, boom, we get the instantaneous rate. This gives us the derivative, a fancy way of saying, how fast is this thing changing right now? Epidemiologists use limits, even if they don't call them that. This math helps guide planning, surge response, and policy changes, even before the final data comes in. Epidemiologists look at the epidemic curve. They see the limit as the number of cases starts small. There's change going on as the number of cases increases, rising to a peak, and then decrease slowly. There's change happening on this side too. In fact, the first derivative is used in an optimization problem to find the maximum number of the curve before it trails off. By formally recognizing this concept, we strengthen decision-making under uncertainty. So next time you're staring at an epidemic curve, wondering if it's peaking, plateauing, or playing tricks on you, ask yourself, what's the limit? Because in public health, limits aren't just about math. They're about saving lives with smarter decisions. That's the power of calculus in action, keeping communities safer, one curve at a time.